It's often easy to overlook the impact that a good camera can have, especially on a 2D platformer. Modern games of the genre usually all have subtle complexities on their cameras to give a good game feel to the character controller. Hollow Knight is no different. The camera not only is adapted to the movement of the knight, but even crazier is how the movements and the boundaries of the camera are in part influenced by the level design. So before we even touch Unreal, I want to take a moment to break down each component of Hollow Knight's camera. Welcome to the Game Dev Pantry, a series where we analyze and reproduce interesting mechanics in Unreal Engine 4. This is part 4 of our series on Hollow Knight's 3 Cs. Today, we're focused entirely on the camera of Hollow Knight, and boy is there a lot to talk about. Let's begin by looking at the idle position. We can see that at its core, Hollow Knight's camera will attempt to keep the knight in the center of the horizon, with one key detail. The camera has a slight bias towards the direction that the knight is facing. It's quite easy to notice if you simply perform a couple of turnarounds. The bias is very subtle as to not feel out of place or disruptive, but nonetheless serves a few purposes. First, it helps contextualize the knight's position by giving an indication of where he's looking. But it also makes things that are relevant pop into the screen earlier, since the direction the knight is looking at is often the direction he's traveling towards. These biases also help counteract the unwanted effect of the next feature of our camera, interpolation. Interpolation, or lerp, is the behavior of a camera that doesn't snap to the pawn, and instead attempts to follow it at a certain speed. How these usually work is that the further the camera is from the player, the faster it will travel. This creates an ease-in effect which helps intensify the impact of movements. A jump, for example, is much more felt when the camera doesn't immediately track the pawn. This also grants time for the player to adapt to the change in scenery. In Hollow Knight, there are multiple speeds used for interpolation. The up direction is a fixed interpolation, which accentuates the feel of the jump. The downward movement has a much higher travel rate, acting almost like a snap when the player is falling. The reason for that is that you want the player to know where he's going to fall. Besides, there's less need to communicate the impact of gravity, as it isn't an action that the player physically performs, so there is no need for instant feedback. As for the left and right movement, there are two speeds. A slow speed for when the player isn't moving, as well as a fast speed for when the player is moving in order to keep up with the dash, while still letting it feel impactful. When the player is dashing, you want the camera to lag a bit more behind, to showcase the jerk without dizzying the player. As we can see, just in the way that the camera keeps up with the pawn, we have a lot of work to do. All these effects are there to complement the movement of the knight and help them feel more impactful without feeling too twitchy. This way of doing camera is quite popular in modern platformers, with the likes of Ori and Celeste having similar behaviors in their camera. It overall feels smoother this way. However, my favorite feature of Hollow Knight's camera is something entirely different, and it has to do with how they handle camera bounds. But to talk about them, we first need to head back to one of the game's ancestors, the Metroids. We're looking mostly at Super Metroid, the paradigm of the Metroidvania genre. If we take a look at the architecture of the levels in this game, we notice that they are comprised of interconnected boards, squares or rectangles. This is reflected in the map, which presents each room in those shapes. This is also how the levels are loaded. Whether it was a restriction of the time's technology or a conscious design choice, the end result is that, since only one room existed at a time, the camera was constrained to the bounds of that room. Let's talk about what that property can bring to a level. The main thing is that the camera is always capturing things that are relevant to the gameplay. There is no need to look at the next room until the player steps into it anyway. It also helps the player with platforming and exploration by providing subtle landmarks in the form of hard walls and grounds. The camera won't go below the ground of the loaded room or beyond the wall of said room. This tells the player, these are the bounds within which important things are. This can be a starting point for exploring thoroughly the room. Of course, if you've played Super Metroid or Hollow Knight, you can probably guess the other side of the metal of this message that the bounds tell the player. Because in those games, it is also what allows level designers to put in secret doors. Since the size of a room is communicated to the player through the bounds of the camera, and that the surrounding areas aren't considered by said camera, there is nothing but the doors to tell the player that there is another room on the other side. Therefore, if you put a room behind a fake wall or a hidden block, the player has to look for it in order to know there is something behind. Since exploration and secret finding is a core fantasy of the genre, this feature is extremely important. There is another overlooked advantage to that method of organizing rooms and fixing camera, and it has to do with navigation. Picture these Super Metroid rooms. A game about exploration thrives on giving possibilities to the player. In a 2D game, you're restricted to up, down, left, or right as options of exploration. However, you'll notice if you look carefully that normally Samus wouldn't be able to make the jump to reach the room up. This would normally severely limit the design space for rooms going up or down. Of course, in the actual game, she can reach those rooms. This is because the game separates both areas with a loading screen, and moves the player from one part to the other as soon as Samus goes through the door. You'll notice that Hollow Knight does the same thing, bridging rooms together with a loading screen, making it seem like the knight can jump a lot higher than he normally can. This allows designers a lot more freedom when creating architectures for their level. All of these features I talked about are present in Super Metroid. So how does Hollow Knight improve on the concept? Well, first, the game is much less restricted in the size of the rooms that they can load, thanks to the progress of technology. This brings a whole new slew of possibilities, but also challenges. In Hollow Knight, the rooms are not only bigger, but are also more architecturally complex. Therefore, for the bounds to be meaningful, the camera not only had to be restricted to the bounds of the loaded room, which can often be massive, but it also needed to be contextually constrained. Let's look at a few examples. Here, the path leading up to the shaman's hut is all one giant room as far as loading is concerned. But you'll notice that when you're next to the entrance of the hut, which is on top of the path, the camera will not try to look below the ground, even though there's technically stuff below. If we move towards the area where we can drop down, we can see that the camera is also dropping down. In other words, each room, on top of the usual constraints around the edges of it, also contains sub-constraints in order to allow the camera to focus on what's relevant. In our example, when the knight is here, the player doesn't care what's below. It's more important to keep the ground at the bottom of the screen. It also reduces the amount of nothing that is shown on the screen. The implementation is relatively simple. We can imagine that the room is divided into squares and rectangles, kinda like rooms in Super Metroid. Within those divisions, the level designer can define which of the edges are actively trying to constrain the camera. In this example, the bound here would only have an edge on the floor. We can see that once we leave that rectangle, the camera returns to trying to keep the player in the vertical center. Another obvious implementation of this method can be seen in this area in Crystal Peak. Here, the bounds would be around this place, and their use is simply to keep the ground on the lower edge of the screen. This is one of the few places in Hollow Knight where we can really feel the camera bounds, and it is in fact the area that prompted the creation of the video on Hollow Knight's camera. The tool used to constrain the camera is very versatile, and gives the level designers not only freedom in how the architecture of the level can be, but also how it is shown to the player. These two key points give rise to a very interesting possibility, especially for a Metroidvania, a possibility that Hollow Knight uses to the fullest: hidden areas. These areas act a bit like hidden entrances to rooms in Super Metroid, but uses the contextual camera bounce to their advantage, which allows the hidden area to be in the same room. We can see that the camera acts as if there was nothing beyond this wall, until the player steps out of the camera bound, which is accompanied with the classic jingle of the game. This method is great because it gives the player instant feedback when they find a room, and doesn't need to make them navigate through convoluted environments, unlike hidden rooms of Super Metroid. In my opinion, it also allows the designer to give hints to the existence of hidden rooms without it being too obvious or too subtle. I could go on and on about the uses of this mechanic, hiding exits from gauntlets or shortcuts, hinting the player of important things, keep focus on the action during boss fights, or help the camera remain stable during hard platforming section. The tool is incredible and the possibilities endless. So how do we reproduce all of this in Unreal? We're going to need to manipulate the position of the camera based on a lot of different factors. To better compartmentalize those functionalities, we took the decision of creating an actor component that will be attached to the pawn. One of the things that is going to influence the movement of the camera is those camera bounds I talked about earlier. So we've also made an actor consisting of a box collider that will act as the camera bounds. We initialize our actor component with a few variables, a reference to the actor and to its camera, and we also set the distance of the camera from the player, and then detach the camera from the knight, since we'll move it using our own logic. So let's recap what we need this camera to do. We want the idle position to have a slight bias towards where the knight is looking. Vertically, we want the camera to have a lerp when the player is going up, and almost snap to the player when he's going down. Horizontally, we want somewhat of a strong lerp, unless the player isn't moving or is currently wall jumping, where we want the lerp to be much weaker. Finally, we want the camera to be bound to the edges of the level, and contextually, based on the desires of the level designer. So we'll have to build tools to help for that. Most of these actions will end up with a set world location of the camera, fired on tick. Since horizontal and vertical movement use different logic and behaviors, we've decoupled those. As for the distance between the camera and the player in terms of depth, it needn't change. I mentioned earlier that the camera would be displaced using a lerp. Since we're updating the camera position each frame, we decided to use Interp 2 function. It acts like a lerp that compensates for the changing tick rate of the game. We're going to use one for each axis. The argument current, as well as the delta time, are easy to get and pass, of course. But let's focus on what our target position needs to be. Let's first look at what it should be without taking the camera bounds into account. In its purest form, the camera should attempt to keep the character in the center, with some slight modifications. We need two biases, one for left-right that I talked about earlier, and one for the down position. The down bias is simply a float that we add to the Z position. For the left-right, we use a float that we multiply either by 1 or -1, depending on whether the character is looking left or right. To get that information, we simply set a look right boolean when the player changes look direction. Simple. With this, we can get the coordinates of where the camera needs to be, if there were no bounds. Therefore, we now need to see how to clamp those coordinates. We use 4 floats for the 4 corners that would be bound. We're also using an array of camera bounds for the component to consider when calculating those bounds. When the component begins overlap with the player, it adds itself to the array and removes itself when the overlap ends. It also fires a function in the component that tells it to update the boundaries data. Let's take a look at how the boundaries data is stored and set. We have again 4 floats there to store the information about the boundaries of that specific camera bound actor. We set those at construction script using a for each with the direction enum we created in a previous episode. To refresh your memory, it's simply an enum with the 4 cardinal directions of 2D. Up, down, left, and right. For each of the directions, we set the corresponding float based on one of 2 things. The first value is simply the size of the collider. In other words, the collider also represents the bounds of the camera. The second thing is technically infinite, and is chosen if a boolean called bridge is true. We have one of those for each direction. The point of the bridge boolean is to set the boundary much further away than the size of the box. This will be useful to connect 2 camera boundaries without creating a jerk. We have a last set of variables to talk about. Another set of booleans that will tell the camera movement if they should consider that direction from that specific actor when calculating the boundaries. As we talked earlier, certain boundaries would only exist for one specific direction. The final thing is a layer integer to allow bounds, bridges in particular, to have priority over others. This covers the actor part of the camera bound. We can place those in the level with different properties, and they will do the rest. Let's head back to the camera movement component to take a look at the function that updates the boundaries based on the new camera bound actors. This function checks each camera bound actor in the list and will assign a boundary for each direction based on these criteria. First, for each direction, it will ignore the data of an actor if said direction is set to false. Then, it will prioritize the boundary of an actor with the highest layer. Finally, should the layers be of equal value, the function will prioritize the lowest absolute value being presented, therefore the most constraining value. It's important to note that we're using local variables to compare these, and we initialize them with a ridiculously high or low value. Once those loops are done, we set the actual bounds float at the end of the function. Now that they're set, we can use those floats to clamp the camera's target position. How we proceed is simply by taking the boundary value, adding the difference from the edge of the camera vision to the center, and setting this as clamp. Since the field of view is 90 degrees, and the aspect ratio is 16:9, for horizontal, this difference amounts to the distance of the player from the camera, and for vertical, it is that same distance times 9/16. The output of the clamped camera target is used as the target for the interp function. The final thing to take a look at is how we modulate the interp speed. It's important to understand what this value represents roughly. A value of 1, for example, means that it should take about 1 second to cover half the distance between the current and the target. The reality is, this is slightly dependent on the tick rate. For example, at a frame rate of 60 per second, in 1 second, 60% of the distance will be crossed. A value of 2 would mean that in 1 second about 75% of the distance will be crossed. 3 would be 83%, and so on. With this in mind, let's take a look at how we modulate this speed value, beginning with the vertical movement. This one is rather simple. If the camera is higher than it should be, and the knight has downwards velocity, the interp should be incredibly fast. Otherwise, it should be a smooth lerp. I found that 3.5 was the just right value for smoothness. The horizontal interp speed has a bit more moving parts. The first thing present is a failsafe should the player move too far away from the camera, so that it always keeps up. The other thing is, we want to distinguish the interp speed between when the player is moving and standing still. When moving, we want the camera to keep up a bit faster, whereas when standing still, we can let it be much slower. The final thing has to do with the wall jump. When the player wall jumps, we don't want the camera to move left and right frantically. Therefore, when the player is in wall jump initial, the first few moments of the wall jump, the interp speed will be much slower. With this, we've covered every element of what the basic camera movements in Hollow Knight looks like. We can even build a little mock-up area using the tools we've made. Here, I have 2 rooms and a hidden one. I use a bridge between the 2 rooms, and no bridge for the hidden room, to create that jerk effect and hidden room effect. Here's the result. Thanks again for joining us for this rather lengthy episode of the Game Dev Pantry. We hope you've learned a thing or two about the cameras in 2D platformers. Remember, you can always grab the project if you want to take a look at how it's done in more details. We're almost done with Hollow Knight. The next episode will talk about a few polished features you can have in a 2D platformer, as well as how we would design and implement a new power-up for Hollow Knight, using the game's approach to power-ups.